People are interested in answering many types of questions, especially the researchers. For example, a scientist might want to know whether the earth is warming up, or a physician might want to know whether a new medication will lower a person's blood pressure. An educator might wish to see whether a new teaching technique is better than a traditional one. A retail merchant might want to know whether the public prefers a certain color in a new line of fashion. These types of questions can be addressed through statistical hypothesis testing. In this video, hypothesis testing will be discussed. Before we proceed to the discussion, let's have the objectives first. After completing this chapter, you should be able to first understand the definitions used in hypothesis testing. State the null and alternative hypothesis. Find critical values for the z-test. State the 5 steps used in hypothesis testing. Test means when S is known using the z-test. Test means when S is unknown using the t-test. Test proportions using the z-test. Test variances or standard deviations using the chi-square test. Test hypothesis using confidence intervals. Explain the relationship between type 1 and type 2 errors and the power of a test. Hypotheses concerning parameters such as means and proportions can be investigated. There are 2 specific statistical tests used for hypothesis, the z-test and the t-test. But first, let us talk about the 3 methods used to test hypotheses. These are: first is the traditional method, second is the p-value method, and third is the confidence interval method. Traditional method has been used since the hypothesis testing method was formulated. So this is the first method used since hypothesis testing method was being formulated. The second method, which is the p-value method, is the newer method in which it became popular with the advent of modern computers and high-powered statistical calculators. And the third is the confidence interval method, which is a method that illustrates the relationship between hypothesis testing and confidence intervals. Among the 3, let's go first to the traditional method, which is the first one. So in every hypothesis testing, situation begins with a statement of a hypothesis. So a statistical hypothesis is a conjecture about a population parameter. This conjecture may or may not be true. There are 2 types of statistical hypothesis. It is the null hypothesis and the alternative hypothesis. The null hypothesis, symbolized by H sub 0, it is a statistical hypothesis that states that there is no difference between a parameter and a specific value, or there is no difference between 2 parameters. The other one is the alternative hypothesis, symbolized by H sub 1. It is a statistical hypothesis that states the existence of a difference between a parameter and specific value, or states that there is difference between 2 parameters. As an illustration of how hypothesis should be stated, 3 different statistical studies will be used as examples. So the first example or situation A. A medical researcher is interested in finding out whether a new medication will have any undesirable side effects. The researcher is particularly concerned with the pulse rate of the patients who take the medication. Will the pulse rate increase, decrease, or remain unchanged after a patient takes the medicine? Since the researcher knows that the mean pulse rate of the population under study is 82 beats per minute, the hypotheses for this situation are like this. H sub 0 is 2 equals 82, or that is the null hypothesis, and the alternative hypothesis is not equal to 82. The null hypothesis specifies that the mean will remain unchanged, and the alternative hypothesis states that it will be different or it is changing. This test is called a two-tailed test, since the possible side effects of the medicine could be to raise or lower the pulse rate. So the second one, or in this situation B, a chemist invents an additive to increase the life of an automobile battery. If the mean lifetime of the automobile battery without that additive is 36 months, then her hypotheses are like this. In this situation, the chemist is interested only in increasing the lifetime of the batteries. So her alternative hypothesis is that the mean is greater than 36 months. The null hypothesis is that the mean is equal to 36 months. This test is called a right-tailed, since the interest is in an increase only. The third, or situation C. A contractor wishes to lower heating bills by using a special type of insulation in houses. If the average of the monthly heating bills is $78, her hypothesis about heating costs with the use of insulation are like this. This test is a left-tailed test since the contractor is interested only in lowering heating costs. This clearly shows that three different statistical studies, which is the two-tailed test, the right-tailed test, and the left-tailed test. One. The other one is the hypothesis testing common phrase. This is helpful or useful in translating verbal conjectures into mathematical symbols. Here is where the concepts of statistical test and level of significance are used. A statistical test uses the data obtained from a sample to make a decision about whether the null hypothesis should be rejected. The numerical value obtained from a statistical test is called the test value. In this type of statistical test, the mean is computed for the data obtained from the sample and is compared with the population mean. Then a decision is made to reject or not reject the null hypothesis on the basis of the value. If the difference is significant, the null hypothesis is rejected. If it is not, then the null hypothesis is not rejected. In the hypothesis testing situation, there are four possible outcomes. The four possible outcomes are shown like this. There are two types of error, the type 1 error and the type 2 error. A type 1 error occurs if you reject the null hypothesis when it is true. A type 2 error occurs if you do not reject the null hypothesis when it is false. Like in this example, the hypothesis testing situation in a jury trial. In a jury trial, there are four possible outcomes. The defendant is either guilty or innocent, and he or she will be convicted or acquitted. Now, the hypotheses are these two. The null hypothesis is the defendant is innocent, while the alternative hypothesis, the defendant is not innocent. Next, the evidence is presented in court by the prosecutor, and based on this evidence, the jury decides the verdict innocent or guilty. If the defendant is convicted but he or she did not commit the crime, then a type 1 error has been committed. It is seen in the block 1, the first block. On the other hand, if the defendant is convicted and he or she has committed the crime, then a correct decision has been made. It is seen in the block 2. If the defendant is acquitted and he or she did not commit the crime, a correct decision has been made by the jury. It is seen in the block 3. However, if the defendant is acquitted and he or she did commit the crime, then a type 2 error has been made. It is in the block 4. The decision of the jury does not prove that the defendant did or did not commit the crime. The decision is based on the evidence presented. If the evidence is strong enough, the defendant will be convicted in most cases. If the evidence is weak, then the defendant will be acquitted in most cases. Nothing is proved absolutely. Likewise, the decision to reject or not reject the null hypothesis does not prove anything. The only way to prove anything statistically is to use the entire population, which in most cases is not possible. The decision then is made on the basis of probabilities. That is why there is a large difference between the mean obtained from the sample and the hypothesized mean. The null hypothesis is probably not true. The question is, how large a difference is necessary to reject the null hypothesis? Here is where the level of significance is used. Is level of significance. The level of significance is the maximum probability of committing a type 1 error. This probability is symbolized by a Greek letter alpha. It is like this. The probability of a type 2 error is symbolized by the Greek letter beta. It is also like this. In most hypothesis testing situations, it cannot be easily computed which is the type 2. However, type 1 and type 2 are related in that decreasing one increases the other. Statisticians generally agree on using three arbitrary significance levels, the 0.10, the 0.05, and the 0.01 levels. That is, the null hypothesis is rejected. The probability of a type 1 error will be 10%, 5%, or 1% depending on which level of significance is used. In another way of putting it, when a 0.10, there is 10% chance of rejecting the true null hypothesis. When a 0.05, there is a 5% chance of rejecting a true null hypothesis. And when a 0.01, there is 1% chance of rejecting a true null hypothesis. After a significance level is chosen, a critical value is selected from a table for the appropriate test. If a z-test is used, for example, the z-table is consulted to find the critical value. The critical value determines the critical and non-critical regions. So what is critical value, critical region, and non-critical region? The critical value separates the critical region from the non-critical region. The symbol for critical value is CV. The critical region is the range of values of the test value that indicates that there is a significant difference and the null hypothesis should be rejected. The non-critical or non-rejection region is the range of values of the test value that indicates that the difference was probably due to chance and that the null hypothesis should not be rejected. The critical value can be on the right side of the mean or on the left side of the mean of a one-tailed test. Its location depends on the inequality sign of the alternative hypothesis. So let's have an example. Finding the critical value for type 1 error, which is 0.01, it is a right-tailed test. To find the critical region, we will base on the z-table. Since 0.01 is equal to 1%, then we will find a z-value such that 1% of the area falls to the right of the value and 99% falls to the left of the value. Using the z-table, the critical z-value is 2.33 since the value gives the area closest to 0.990, so that is 0.9901. So here is the figure that shows the critical and non-critical regions and the critical value. So next, let's proceed to two-tailed test. In a two-tailed test, the null hypothesis should be rejected when the test value is in either of the two critical regions. For a two-tailed test, then the critical region must be split into two equal parts. If a 0.01, then 1/2 of the area or 0.005 must be to the right of the mean and 1/2 must be to the left of the mean, as shown in this figure. In this case, the z-value on the left side is found by looking up the z-value corresponding to an area of 0.0050. The z-value falls about halfway between 2.57 and 2.58 corresponding to the areas of 0.0049 and 0.0051. The average of 2.57 and 2.58 is 2.575, so if the z-value is needed to 3 decimal places, 2.575 is used. However, if the z-value is rounded to 2 decimal places, 2.58 is used. On the right side, it is necessary to find the z-value corresponding to 0.99, 0.005, or 0.9950. Again, the value falls between 0.9949 and 0.9951. So we have 2.58. So these are the other similar procedures used to find the other values. With rejection regions shaded shows the critical value or the CV For the three situations discussed in section for values of 0.10, 0.05, and 0.01, the procedure for finding critical values is outlined next, where k is a specified number. Here are the steps in finding the critical value for specific probability of type 1 error values using the z-table. So first step, draw the figure and indicate the appropriate area. If the test is left-tailed, the critical region with an area equal to value will be on the left side of the mean. If the test is right-tailed, the critical region with an area equal to a value will be on the right side of the mean. If the test is two-tailed, the value must be divided by 2. One half of the area will be to the right of the mean and one half will be to the left of the mean. The second step, for a left-tailed test, use the z-value that corresponds to the area equivalent to a z-table. For the right-tailed test, use the z-value that corresponds to the area equivalent to 1 minus the value. For a two-tailed test, use the z-value that corresponds to a over 2 for the left value. It will be negative. For the right value, use the z-value that corresponds to the area equivalent to 1 over a over 2, 1 minus a over 2. It will be positive. So let's have an example. A left-tailed test with value of 0.10. So here is the solution. Step 1. Draw the figure and indicate the appropriate area. Since this is a left-tailed test, the area of 0.10 is located in the left tail, as shown in this figure. So the second step, find the area closest to 0.1000 in z-table. In this case, it is 0.10027 or 0.1003. So find the z-value that corresponds to the area. It is negative 1.28. We use negative values z-table since it is a left-tailed test. So here are the other examples. In hypothesis testing, the following steps are recommended. First, state the hypothesis. Be sure to state both the null and alternative hypothesis. Second, design the study. This step includes selecting the correct statistical test, choosing a level of significance, and formulating a plan to carry out the study. The plan should include information such as the definition of the population, the way the sample will be selected, and the methods that will be used to collect the data. Step 3. Conduct the study and collect the data. Step 4. Evaluate the data. The data should be tabulated in this step. The statistical test should be conducted. Finally, decide whether to reject or not reject the null hypothesis. The last step, summarize the results. And now let's proceed to the z-test for a mean.
In this chapter, two statistical tests will be explained, the z-test and the t-test. Z-test is used when the population standard deviation is known, while t-test is used when the population standard deviation is unknown. Many hypotheses are tested using a statistical test based on the following formula. Test value is equal to observed value minus expected value over standard error. Note that the observed value is the statistic such as the mean that is computed from the sample data. The expected value is the parameter such as the mean that you would expect to obtain if the null hypothesis were true. In other words, the hypothesized value. The denominator is the standard error of the statistic being tested. In this case, the standard error of the mean. The z-test is a statistical test for the mean of a population. It can be used when n is greater than or equal to 30, or when the population is normally distributed and the population standard deviation is known. Formula for the z-test is z is equal to the sample mean minus hypothesized population mean over population standard deviation divided by the square root of the sample size. So let's have an example problem, and we must use the 5 steps for solving in hypothesis testing problems. A researcher reports that the average salary of assistant professor is more than $42,000. A sample of 30 assistant professor has a mean salary of $43,260. At an alpha 0.05 tests the claim that assistant professors earn more than $42,000 per year. The standard deviation of the population is $5,230. So let's now solve the problem. Step 1. State the hypothesis and identify the claim. Our null hypothesis is mu equals to $42,000, and the alternative hypothesis is mu is greater than $42,000. That is the claim. Step 2. Let's find the critical value. Since the alpha is 0.05 and the test is the right-tailed test, the critical value is z is equal to positive 1.65. Step 3. Let's compute the test value. So z is equal to sample mean minus hypothesized population mean over population standard deviation divided by 2 the square root of sample size. So our sample mean here is $43,260 minus $42,000 over 5,230 divided by 2 the square root of 30. So our answer is 1.32. Step 4. Make the decision. Since the test value is 1.32 is less than the critical value, positive 1.65, and it's not in the critical region, the decision to not reject the null hypothesis. This is summarized in the figure below. Step 5. Summarize the result. There is not enough evidence to support the claim that assistant professor earn more average than $42,000 per year. Let's have another example for the two-tailed test. The Medical Rehabilitation Education Foundation reports that the average cost of rehabilitation for stroke victims is $24,672. To see if the average cost of rehabilitation is different at a particular hospital, a researcher selects a random sample of 35 stroke victims at the hospital and finds that the average cost of their rehabilitation is $25,226. The standard deviation of the population is $3,251. At an alpha 0.01 can be it concluded that the average cost of stroke rehabilitation at a particular hospital is different from $24,672. So let's now solve this problem. Our null hypothesis is mu is equal to $24,672, and our alternative hypothesis is mu is not equal to $24,672. That is our claim. Step 2. Find the critical value. Since our alpha is 0.01 and the test is two-tailed test, the critical values are positive 2.58 and negative 2.58. Step 3. So let's now compute the test value. So z is equal to the sample mean 25,226 minus the hypothesized population mean 24,672 over the population standard deviation 3,251 divided by the square root of the sample size 35 is equal. So overall the answer is 1.01. So our decision here is to do not reject the null hypothesis since the test value falls in the non-critical region, as shown in the figure below. So therefore, there is not enough evidence to support the claim that the average cost of rehabilitation at a particular hospital is different from $24,672. Note that the claim can be either the null or alternative hypothesis, and one should identify which it is. After the study is completed, the null hypothesis is either rejected or not rejected. From these two facts, the decision can be identified in the appropriate block. Please read in your mind the figure below. So let us now proceed to another topic, which is the p-value method for hypothesis testing. P-value is the probability of getting a sample statistic or a more extreme sample statistic in the direction of the alternative hypothesis when the null hypothesis is true. In solving hypothesis testing problems using the p-value method, we can follow this formula. Now let's try to solve a problem. A researcher wishes to test the claim that the average cost of tuition and fees at a four-year public college is greater than $5,700. She selects a random sample of 36 four-year public college and finds the mean to be $5,950. The population standard deviation is $659. Is there enough evidence to support the claim at an alpha 0.05? Use the p-value method. To solve this problem, we have the null hypothesis as mu is equal to $5,700 and the alternative hypothesis is mu is greater than $5,700. This is the claim. To compute the test value, we have the formula and we must distribute the following given to the formula. So we have 5,950 minus 5,700 over 659 divided by the square root of 36. So the answer is equal to 2.28. Step 3. Let's find the p-value. Using the table E and appendix C, find the corresponding area under the normal distribution for Z is equal to 2.28. So it is 0.9887. Subtract this value for the area from 1.0000 to find the area in the right tail. So 1.000 minus 0.9887 is equal to 0.0113. Hence, the p-value is 0.0113. Let's make the decision. Since p-value is less than 0.05, the decision is to reject the null hypothesis. And therefore, there is enough evidence to support the claim that the tuition and the fees at four-year public college are greater than $5,700. To make the decision whether to reject the null hypothesis, you can use the following rule. The decision rule when using a p-value. So if p-value greater than or equal to alpha, we reject the null hypothesis. And if p-value is strictly greater than alpha, do not reject the null hypothesis. We also have a guidelines for p-values. But be advised that these guidelines are not written in stone, and some statisticians may have other opinion. So here are guidelines. If p-value is less than or equal to 0.01, reject the null hypothesis. The difference is highly significant. If 0.01 is less than the p-value, but p-value is less than or equal to 0.05, reject the null hypothesis. The difference is significant. If 0.05 is less than the p-value, but p-value is less than or equal to 0.10, consider the consequence of type 1 error before rejecting the null hypothesis. If p-value is greater than 0.10, do reject the null hypothesis. The difference is not significant. Let's move on to another topic, which is the t-test for a mean. When the population standard deviation is unknown, the z-test is not normally used for testing hypotheses involving means. A different test called the t-test is used. The distribution of the variable should be approximately normal. Before we proceed, can you recall the similarities of the t-distribution and the standard normal distribution? You can write your answer in the comments section. If the t-distribution and the standard normal distribution have similarities, they also have differences. So they differ in the following ways. First, the variance is greater than 1. The t-distribution is a family of curves based on the degrees of freedom, which is a number related to sample size. And lastly, as the sample size increases, the t-distribution approaches the normal distribution. The formula for the t-test is t is equal to the sample mean minus the hypothesized population mean over the standard deviation divided by the square root of sample size. The degrees of freedom are df is equal to n minus 1. The formula for the t-test is similar to the formula for the z-test. But since the population standard deviation is unknown, the sample standard deviation is used instead. The critical values for t-test are given in Table F and Appendix C. For a one-tailed test, find the significance level by looking at the top of the row of the table. And finding the appropriate column, find the degrees of freedom by looking down the left column. So let's have an example. Find the critical t-value for alpha 0.05 with the degrees of freedom 16 for a right-tailed t-test. So for this solution, we find the 0.05 column in the top of the row and the 16 in the left-hand column. Where the row and column meet, the appropriate critical value is found. It is positive 1.746. When you test hypothesis by using the t-test or traditional method, follow the same procedure as for the z-test except use the Table F. Let's have an example problem. A medical investigation claims that the average number of infections per week at a hospital in southwestern Pennsylvania is 16.3. A random sample of 10 weeks had a mean number of 17.7 infections. The sample standard deviation is 1.8. Is there enough evidence to reject the investigator's claim at an alpha 0.05? So let's solve the problem. Our null hypothesis is mu is equal to 16.3. That is our claim. And the alternative hypothesis is mu is not equal to 16.3. Step 2, the critical values are positive 2.262 and negative 2.262 for an alpha 0.05 and the degrees of freedom equals to 9. So let's now solve the test value. Our sample mean here is 17.7. Our hypothesized population mean is 16.3 and the sample standard deviation is 1.8 and the sample size is 10. So 17.7 minus 16.3 over 1.8 divided by the square root of 10 is equal to 2.46. So our decision here is to reject the null hypothesis since 2.46 is greater than 2.262. So therefore, there is enough evidence to reject the claim that the average number of infections is 16.3. Students sometimes have difficulty deciding whether to use the z-test or t-test. The rules are the same as those pertaining to confidence interval. So number 1, if population standard deviation is known, use the z-test. The variable must be normally distributed if n is less than 30. Number 2, if population standard deviation is unknown but n is greater than or equal to 30, use the t-test. Number 3, if population standard deviation is unknown and n is less than 30, use the t-test. The population must be approximately normally distributed.
Hello everyone, I am Jerian Madis and I am the one who assigned to report to you about the z-test for a proportion. So from our discussion last week in chapter 7, proportion is the same as a percentage of the population. So let us recall that the mean is equal to NP and the standard deviation is the square root of N, P, and Q. That is for the binomial distribution. Since a normal distribution can be used to approximate the binomial distribution when NP is greater than or equal to 5 and the NQ is greater than or equal to 5, the standard normal distribution can be used to test hypothesis for proportion. So from the formula for the z-test for proportion, as what you can see in the picture above, z is equal to sample proportion minus population proportion over the square root of sample proportion and the population proportion over sample size. The formula is derived from the normal approximation to the binomial and follows the general formula. Test value is equal to the observed value minus expected value over the standard error. The formula z is equal to the observed value minus the expected value over the standard error can be derived from the formula z is equal to x minus the mean over the standard deviation. By substituting, mean is equal to NP and the standard deviation is the square root of NP and Q. And then dividing both numerator and denominator by n. There are three assumptions for testing a proportion. Number one is the sample is a random sample, and the two is the conditions for the binomial experiment are satisfied, and the third is NP greater than or equal to 5 and the NQ is greater than or equal to 5. So level A is used to find critical values and p-values. So for us to understand more, we have an example. A dietitian claimed that 60% of people are trying to avoid trans fats in their diets. She randomly selected 200 people and found that 128 people stated that they were trying to avoid trans fats in their diets. At the alpha is equal to 0.05, is there enough evidence to reject the dietitian's claim? So for our solution, the step 1, state the hypothesis and identify the claim. So our hypothesis is P is equal to 0.60, where it is their claim, and P is not equal to 0.60. For our step 2, find the critical values. Since alpha is 0.05 and the test value is 212, the critical values are positive or negative 1.96. So in the step 3, let us compute the test value. In our step 3, compute the test value. So it is necessary to find the observed value. So observed value is equal to x over n, where our x is 122 and in our n is 200. So 128 divided by 200 is 0.64. So our P here is the 0.60 and our Q is 1 minus 0.60 equal to 0.40. So we have to substitute from the formula. So Z is equal to observed value minus the P over the square root of PQ over N. So 0.64 minus 0.60 over square root of 0.60 times 0.40 over the n, which is 200. So if we calculate it in our calculator, we have a result of 1.15. So in our step 4, we will make the decision. So let us not reject the null hypothesis since the test value falls outside the critical region as what we have seen in the graph above. So in our step 5, let us summarize the results. There is not evidence to reject the claim that 60% of the people are trying to avoid trans fat in their diets. In our example, a statistician read that at least 77% of the population opposed replacing 1 bills with 1 coins. To see if the claim is valid, the statistician selected a sample of 80 people and found that 55 were opposed to replacing the 1 bills at alpha is equal to 0.1. So
So, test the claim that at least 77% of the population are opposed to the change. So, in our solution, in our step 1, state the hypothesis and identify the claim. So, our claim here is P is equal to 0.77, and the second hypothesis is P is less than 0.77. In our step 2, find the critical value. Since alpha is 0.01 and the test is left tail, the critical value is negative 2.33. So in our step 3, compute the test value. So our observed value is equal to x over n, where x is equal to 55 and n is equal to 80. If we will compute to our calculator, we have the result 0.6875. And our expected value is equal to 0.77, and Q is equal to 1 minus 0.77 or 0.23. So let us substitute it in our formula. So C is equal to observed value minus the expected value over the square root of PQ over N. It is equal to 0.6875 minus 0.77 over the square root of 0.77 times 0.23 over 80. If we compute it in our calculator, we have the result of negative 1.75. In our step 4, do not reject the null hypothesis, since the test value does not fall in the critical region, as what we have shown in the graph above. In our step 5, there is not evidence to reject the claim that at least 77% of the population oppose replacing 1 bills with 1 coins. For our last example in our Z test for proportion, an attorney claims that more than 25% of all lawyers advertise. A sample of 200 lawyers in a certain city choose that 63 had used some from the advertising. At alpha is equal to 0.05, is there enough evidence to support the attorney's claim? Use the p-value method. So, in our step 1, let us state the hypothesis and identify the claim. So, our hypothesis here is p is equal to 0.25 and p is greater than 0.55, which is the claim. Step 2, compute the test value. So our observed value is equal to x over n, where x is equal to 63 and n is equal to 200. So 63 divided by 200, we have the result of 0.315. So our p here, or the expected value, is equal to 0.25. And our q is equal to 1 minus 0.25, and the result is 0.75. Substituting in our formula, so z is equal to observed value minus the expected value over the square root of pq over n. So 0.315 minus 0.25 over the square root of 0.25 times 0.75 over 200. We have the result of 2.12. So in our step 3, find the p-value. The area under the curve for z is equal to 2.12 is 0.9830. So subtracting the area from 1, you get 1 minus 0.9830 is equal to 0.0170. So the p-value is 0.0170. So in our step 4, let us reject the null hypothesis, since 0.0170 is less than 0.05. So in our step 5, there is enough evidence to support the attorney's claim that more than 25% of the lawyers use some form of advertising. So next, let us proceed to X-squared test for a variance or standard deviation. In Chapter 7, the chi-square distribution was used to construct a confidence interval for a single variance or standard deviation. This distribution is also used to test a claim about a single variance or standard deviation. To find the area under the chi-square distribution, let us use the table G in Appendix C. There are three cases to consider. First, finding the square critical value for a specific alpha when the hypothesis test is right-tailed. Second, finding the chi-square critical value for a specific alpha when the hypothesis test is left-tailed. And the third, find the chi-square critical value for a specific alpha when the hypothesis test is in two-tailed. Let us have an example. So find the critical chi-square value for 15 degrees of freedom when alpha is 0.05 and the test is in the right tail. So that the distribution is shown in the graph. So find the alpha value at the top of the table and find the corresponding degrees of freedom in the left column. The critical value is located there. The two columns met, in this case, 24.996, as what you have seen in the picture above. In our next example, find the critical chi-square values for 22 degrees of freedom when alpha is 0.05 and a two-tailed test is conducted. So, when a two-tailed test is conducted, the area must be split as shown in the graph above. Let us note that the area to the right of the larger value is 0.025 times the 0.05 over 2 or alpha over 2. And the area to the right of the smaller value is 0.975, whereas 1 minus 0.05 over 2 or 1 minus alpha over 2. So let us remember that chi-square values cannot be negative. Hence, you must use alpha values in the table of 0.025 and 0.975. With degrees of freedom, the critical values are 36.781 and 10.982 respectively. When you are testing a claim about a single variance using the chi-square test, there are three possible test equations: right-tailed test, left-tailed test, and the two-tailed test. So, if a researcher believes that the variance of a population to be greater than some specific value, let us say 225, then the researcher states the hypothesis as the population variance is equal to 225. The population variance is greater than 225, that conducts a right-tailed test. If the researcher believes that the variance of a population to be less than 225, then the researcher will state the hypothesis as the population variance is equal to 225, population variance is less than 225, that conducts a left-tailed test. But if a researcher does not wish to specify a direction, she or he states the hypothesis as population variance is equal to 225, population variance is not equal to 225. So the formula for the chi-square test for a single variance is shown in the picture. So x squared is equal to n minus 1 times the sample variance over the population variance. So there are three assumptions are made for the chi-square test as outlined here. So the assumptions for the chi-square test for a single variance is: first, the sample must be randomly selected from the population. Second, the population must be normally distributed for the variable under study. And lastly, the observation must be independent for one another. The traditional method for hypothesis testing follows the same 5-step listed earlier. They are repeated here. So our step 1, state the hypothesis and identify the claim. Step 2, find the critical value. And the step 3, compute the test value. And step 4, make the decision. And lastly, summarize the result. So let us have the example. An instructor wishes to see whether the variation in score of the 23 students in her class is less than the variance of the population. The variance of the class is 198. Is there enough evidence to support the claim that the variation of the students is less than the population variance, where the population variance is equal to 25 at alpha is 0.25? Assume that the scores are normally distributed. So in our step 1, let us state the hypothesis and identify the claim where the population variance is equal to 25 and the population variance is less than 225, which is their claim. So in our step 2, find the critical value. So since that this test is left-tailed and alpha is 0.25, use the value 1 minus 0.05 is equal to 0.95. So the degrees of freedom are n. So n minus 1 is equal to 23 minus 1 is equal to 22. So hence the critical value is 12.338. Note that the critical region is on the left as shown in our figure above. So in our step 3, let us compute the test value. So we will use the formula. So x squared minus n minus 1 times the sample from s squared is equal to the population variance is equal to 23 minus 1 times 198 over 222, and it is equal to 19.36. So in our step 4, make the decision. So since the test value 19.36 falls in the non-critical region as shown in our graph above, the decision is to not reject the null hypothesis. So lastly, let us summarize the result. There is not enough evidence to support the claim that the variation in test scores of the instructor's students is less than the variation in scores of the population. Let us have another example. A hospital administrator believes that the standard deviation of the number of people using outpatient surgery per day is greater than 8. A random sample of 15 days is selected. So the data are shown at alpha is 0.10. Is there enough evidence to support the administrator's claim? Let us assume that the variable is normally distributed. So from the problem given, in our step 1, let us state the hypothesis and identify the claim. So our standard deviation is equal to 8 and greater than 8, which is their claim. So since the standard deviation is given, it should be squared to get the variance. So in our step 2, find the critical value. So since the test is right-tailed with the degrees of freedom of 15 minus 1 is 14 and the alpha is 0.10, the critical value is 21.064. So let us compute the test value. Since raw data are given, the standard deviation of the sample must be found by using the formula in chapter 3 or from our calculator. So it is S is equal to 11.2. So substituting from the formula, x squared minus n minus 1 times s squared over the population variance is equal to 15 minus 1 times 1.2 squared over 64. If we calculate it in our calculator, we have the result of 27.44. So in our step 4, let us make the decision. The decision is to reject the null hypothesis. Since the test value is 27.44 is greater than the critical value, which is 21.064, and falls in the critical value and the critical region as what we have seen in the graph above. So now let us summarize the result. So there is enough evidence to support the claim that the standard deviation is greater than 8. So for more understanding, let's have another example. So a cigarette manufacturer wishes to test the claim that the variance of the nicotine content of its cigarette is 0.644. So nicotine content is measured in milligrams and assume that it is normally distributed. A sample of 20 cigarettes has a standard deviation of 1 milligram at alpha of 0.05. Is there enough evidence to reject the manufacturer's claim? So in our solution, let us state first the hypothesis and identify the claim. So our hypothesis here is that population variance is equal to 0.644, which is the claim, and population variance is not equal to 0.644. So next, find the critical value. Since this test is total test at 0.05 alpha, the critical value for 0.025 and 0.975 must be found. The degrees of freedom are 19, hence the critical values are 32.8, 52, and 8.907 respectively. So the critical or rejection regions are shown in the graph above. So in our step 3, compute the test value. So let us substitute from our formula. X squared is equal to n minus 1 times s squared over the population variance is equal to 20 minus 1 times 1.0 squared over 0.644. If we calculate it in our calculator, we will have the result of 29.5. Since the standard deviation x is given the problem, it must be squared for the formula. So next, let us make the decision. Let us not reject the null hypothesis since the test value falls between the critical values 8.907 is less than 29.5, less than 32.852, and in the non-critical region as shown in our graph above. So lastly, let us summarize the result. There is not enough evidence to reject the manufacturer's claim that the variance of the nicotine content of the cigarettes is equal to 0.644. So for more understanding, let us have another example. So find the p-value when x squared is 19.274 and the n is 8 and the test is in the right tail. So in our solution, to get the p-value, look across the row with the the degree of freedom is equal to 7 in our table and find the two values that 19.274 falls between. So next, find the p-value when x squared is equal to 3.823 where n is equal to 13 and the test is in the left tail. So to get the p-value, let us look across the degree of freedom is equal to 12 and find the two values that 3.823 falls between. So they are 3.571 and 4.404. So look up to the top row and find the values corresponding to 3.571 and 4.404. So they are 0.99 and 0.975 respectively. So when the x squared test falls on the left side, each of the values must be subtracted from 1 to get the interval that p-value falls between. So 1 minus 0.99, the result is 0.01, and 1 minus 0.975, we have the result of 0.025. Hence, p-value falls in the interval 0.01 is less than p-value less than the 0.025. So in our calculator, the p-value we obtained is 0.014. From our example, when the x squared test is total, both interval values must be double. If a total test were between used from our example, then the interval would be 2 times 0.01 less than t value is less than 2 times 0.025. So the p-value method for hypothesis testing for a variance or standard deviation follows the same steps shown in the preceding sections. So from step 1, state the hypothesis and identify the claim, compute the test value, find the p-value, make the decision, and summarize the result. And for the last example, a researcher knows from the past studies that the standard deviation of the time it takes to inspect a car is 16.8 minutes. A sample of 24 cars is selected and inspected. The standard deviation is 12.5 minutes at alpha is equal to 0.05. So, it can be concluded that the standard deviation has changed. So, let us use the p-value method. So, first, our hypothesis is the standard deviation of 16.8 and standard deviation is not equal to 16.8. Where is their claim? So, let us compute the test value. So, x squared is equal to n minus 1 times s squared over the population variance, or equal to 24 minus 1 times 12.5 squared over 16.8 squared, since the given is the standard deviation. Is equal, if we calculate it in our calculator, we have the result of 12.733. So, next, let us find the p-value. So, using our table, with the degrees of freedom is equal to 23 and the value is 12.733 falls between the 11.689 and 13.091, corresponding to 0.975 and 0.95 respectively. So, since these values are found on the left side of the distribution, each value must subtract it from 1. So, hence, 1 minus 0.975 is equal to 0.025 and 1 minus 0.95 is equal to 0.05. So since this is a truth-held test, the area must be doubled to obtain the p-value interval. So 0.05 is less than p-value, less than 0.10 or somewhere between 0.5 and 0.10. So the p-value obtained in the calculator is 0.85. So let us make the decision since alpha is 0.05 and the p-value is between 0.05 and 0.10. Thus the decision is not rejected, the null hypothesis, since p-value is greater than the alpha. So let us summarize the result. There is not enough evidence to support the claim that the standard deviation has changed.
In hypothesis testing, there are several other concepts that might be of interest to students in elementary statistics. These topics include the relationship between hypothesis testing and confidence intervals, and some additional information about the type 2 error. There is a relationship between confidence intervals and hypothesis testing. When the null hypothesis is rejected in a hypothesis testing situation, the confidence interval for the mean using the same level of significance will not contain the hypothesized mean. Likewise, when the null hypothesis is not rejected, the confidence interval computed using the same level of significance will contain the hypothesized mean. For example, sugar is packed in 5-pound bags. An inspector suspects the bags may not contain 5 pounds. A sample of 50 bags produces a mean of 4.6 pounds and a standard deviation of 0.7 pound. Is there enough evidence to conclude that the bags do not contain 5 pounds as stated at alpha is equal to 0.05? Also, find the 95% confidence interval of the true mean. Now, the null hypothesis is mean is equal to 5 and the alternative hypothesis is mean is not equal to 5, which is the claim. The critical values are positive 1.96 and negative 1.96. To compute for the test value, use the formula z is equal to the sample mean minus population mean divided by standard deviation over square root of the sample size. Then substitute 4.6 minus 5 divided by 0.7 over square root of 50 equals negative 0.4 over 0.099. The answer is negative 4.04. Since negative 4.04 is less than negative 1.96, the null hypothesis is rejected. There is enough evidence to support the claim that the bags do not weigh 5 pounds. The 95% confidence for the mean is given by sample mean minus z alpha over 2 times s over square root of n is less than mu, and mu is less than sample mean plus z alpha over 2 times s over square root of n. Substitute 4.6 minus quantity of 1.96 times quantity of 0.7 over square root of 50 quantity is less than mu and is less than 4.6 plus quantity of 1.96 times quantity of 0.7 over square root of 50 quantity. The answer is 4.4 is less than mu and mu is less than 4.8. Notice that the 95% confidence interval of the population mean does not contain the hypothesized value mu is equal to 5. Hence, there is an agreement between the hypothesis test and the confidence interval. Another example, a researcher claims that adult hags feed a special diet will have an average weight of 200 pounds. A sample of 10 hags has an average weight of 198.2 pounds and a standard deviation of 3.3 pounds. At alpha 0.05, can the claim be rejected? Also, find the 95% confidence interval of the true mean. The claim null hypothesis is mean equal to 200 pounds and alternative hypothesis is mu not equal to 200 pounds. In this example, the t-test must be used since the population standard deviation is unknown. It is assumed that hog weights are normally distributed. The critical values at alpha 0.05 with 9 degrees of freedom are positive 2.262 and negative 2.262. The test value is t equal to x bar minus mu over s over square root of n. Substitute 198.2 minus 200 divided by 3.3 over the square root of 10. It is equal to negative 1.88 over 1.0436. The answer is negative 1.72. Thus, the null hypothesis is not rejected. There is not enough evidence to reject the claim that the weight of the adult hogs is 200 pounds. The 95% confidence interval of the mean is sample mean minus t alpha over 2 times s over square root of n is less than mu, and mu is less than sample mean plus t alpha over 2 times s over square root of n. Substitute 198.2 minus quantity 2.262 times quantity 3.3 over square root of 10 quantity is less than mu and is less than 198.2 plus quantity 2.262 times quantity 3.3 over square root of 10 quantity. 198.2 minus 2.361 is less than mu and is less than 198.2 plus 2.361. The answer is 195.8 is less than mu and mu is less than 200.6. The 95% interval does contain the hypothesized mean mu is 200. Again, there is agreement between the hypothesis test and the confidence interval. On the other hand, if the null hypothesis is not rejected, then either it is true or a type 2 error has been committed. A type 2 error occurs when the null hypothesis is indeed false but is not rejected. The probability of committing a type 2 error is denoted as beta. The value of beta is not easy to compute. It depends on several things. including the value of alpha, the size of the sample, the population standard deviation, and the actual difference between the hypothesized value of the parameter being tested and the true parameter. The researcher has control over two of these factors, namely the selection of alpha and the size of the sample. The standard deviation of the population is sometimes known as or can be estimated. The major problem then lies in knowing the actual difference between the hypothesized parameter and the true parameter. If this difference were known, then the value of the parameter would be known. And if the parameter were known, then there would be no need to do hypothesis testing. Hence, the value of beta cannot be computed. But this does not mean it should be ignored. What the researcher usually does is to try to minimize the size of beta or to maximize the size of 1 minus beta, which is called the power of a test. The power of a statistical test measures the sensitivity of the test to detect a real difference in parameters if one actually exists. The power of a test is a probability, and like all probabilities can have values ranging from 0 to 1. The higher the power, the more sensitive the test is to detecting a real difference between parameters if there is a difference. In other words, the closer the power of a test is to 1, the better the test is for rejecting the null hypothesis. Is in fact false. The power of a test is equal to 1 minus beta. That is 1 minus the probability of committing a type 2 error. The power of the test is shown in the upper right-hand block. If somehow it were known that beta is equal to 0.04, then the power of a test would be 1 minus 0.04 is equal to 0.96 or 96%. In this case, the probability of rejecting the null hypothesis when it is false is 96%. The power of a test depends on the probability of committing a type 2 error, and since beta is not easily computed, the power of a test cannot be easily computed. The power of a test can be calculated when a specific value of the mean is hypothesized in the alternative hypothesis. For example, let null hypothesis be equal to 50 and let alternative hypothesis be equal to 52. To find the power of a test, it is necessary to find the value of beta. This can be done by the following steps. Step 1. For a specific value of alpha, find the corresponding value of a sample mean using z is equal to x bar minus mu over standard deviation population over the square root of n, where mu is the hypothesized value given in null hypothesis. Use a right-tailed test. Step 2. Using the value of sample mean found in step 1 and the value of mu in the alternative hypothesis, find the area corresponding to z in the formula z is equal to x bar minus mu over standard deviation of population over the square root of n. Step 3. Subtract this area from 0.5. This is the value of beta. Step 4. Subtract the value of beta from 1. This will give you the power of a test. However, there are some guidelines that can be used when you are conducting a statistical study concerning the power of a test. When you are conducting a statistical study, use the test that has the highest power of the data. There are times when the researcher has a choice of 2 or more statistical tests to test the hypothesis. The tests with the highest power should be used. It is important to remember that statistical tests have assumptions that needed to be considered. If these assumptions cannot be met, then another test with lower power should be used. The power of a test can be increased by increasing the value of alpha. For example, instead of using alpha 0.01, use 0.05. Another way to increase the power of a test is to select a larger sample size. A larger sample size would make the standard error of the mean smaller and consequently reduce beta. These two methods should not be used at the whim of the researcher. Before alpha can be increased, the researcher must consider the consequences of committing a type 1 error. If these consequences are more serious than the consequences of committing a type 2 error, then alpha should not be increased. One final comment is necessary. When the researcher fails to reject the null hypothesis, this does not mean that there is not enough evidence to support alternative hypotheses. It may be that the null hypothesis is false, but the statistical test has too low a power to detect the real difference. This chapter introduces the basic concepts of hypothesis testing. A statistical hypothesis is a conjecture about a population. There are two types of statistical hypotheses, the null hypothesis and the alternative hypothesis. The null hypothesis states that there is no difference, and the alternative hypothesis specifies a difference. To test the null hypothesis, researchers use a statistical test. Any test values are computed using test value is equal to observed value minus expected value divided by the standard error. Two common statistical tests for hypotheses about a mean are the z-test and the t-test. The z-test is used either when the population standard deviation is known and the variable is normally distributed, or when population standard deviation is known and the sample size is greater than or equal to 30. When the population standard deviation is not known and the variable is normally distributed, the sample standard deviation is used, but a t-test should be conducted instead. The z-test is also used to test proportions when number of trials times probability of successes is greater than or equal to 5 and number of trials times probability of failure is greater than or equal to 5. Researchers compute a test value from the sample data in order to decide whether the null hypothesis should be rejected. Statistical tests can be one-tailed or two-tailed, depending on the hypothesis. The null hypothesis is rejected when the difference between the population parameter and the sample statistic is said to be significant. The difference is significant when the test value falls in the critical region of the distribution. The critical region is determined by alpha, the level of significance of the test. The level is the probability of committing a type 1 error. This error occurs when the null hypothesis is rejected when it is true. Three generally agreed upon significance levels are 0.10, 0.05, and 0.01. A second kind of error, the type 2 error, can occur when the null hypothesis is not rejected, when it is false. Finally, you can test a single variance by using a chi-square test. All the hypothesis testing situations using the traditional method should include the following steps. Step 1. State the null hypothesis and alternative hypothesis and identify the claim. Second, state an alpha level and find the critical values. Third, compute the test value. Fourth, make the decision to reject or not to reject the null hypothesis. And fifth, summarize the results. All hypothesis testing situations using the p-value method should include the following steps. 1. State the hypothesis and identify the claim. Second, compute the test value. Third, find the p-value. Fourth, make the decision. Fifth, summarize the results. Formula for the z-test for proportions. Z is equal to x minus mu over population standard deviation, or z is equal to p hat minus population proportion divided by the square root of p times q over n. Formula for the chi-square test for variance or standard deviation. Chi-square is equal to the quantity of the sample size minus 1 quantity times sample variance over population variance. Formula for the z-test for means. Z is equal to sample mean minus hypothesized population mean divided by the population standard deviation over the square root of the sample size if n is less than 30. Variable must be normally distributed. Formula for the t-test for means. T is equal to sample mean minus population standard deviation over sample standard deviation over the square root of the sample size if n is less than 30. Variable must be normally distributed.